Yes.
Yes, ma'am.
Thank you. Okay. This webinar is conducting in collaboration with NITK Suratkal for establishing virtual lab in our institution. We'll start the session with a silent prayer. Okay. I invite Mr. Vishnu Shaji, Assistant Professor, Department of Mechanical Engineering, to deliver the welcome speech.
Hello, am I audible?
Yes, sir.
Thank you. Good afternoon, everyone. Virtual Lab is an initiative of Ministry of Education under National Mission on Education through ICT. This webinar is organized in association with NITK Suratkal and is all about uncovering the opportunities of virtual lab for our academic purposes. The resource persons for this webinar are Mrs. Shrestha, Mr. Beryl Thomas, Ms. Aishwarya Heads, and Mr. Rohit Kushwa. They are senior research fellows at NIT. Now I welcome respected principal, Dr. Saji Sebi sir, to this webinar. I also welcome Vice Principal V.N. Krishnachandran sir, Dean Academics, Dr. Sudha ma'am, HODs, and dear faculty members to this webinar. Now I request respected Dean Academics, Dr. Sudha ma'am, to deliver the inaugural address. Thank you. Over to you, ma'am.
Thank you, Vishnu. A very good afternoon to everyone here. In fact, it had been a matter of requirement since a large number of years. Even earlier, when I was the principal, we had tried to start an initiative of this nature to have a virtual lab such that the lab can be a part of every theory course that we are delivering in our institution. But of course, it could not start off because the requirement was not as deep as right now at this point of time when the pandemic is perhaps getting into our normal classes, especially the laboratory classes. So we are very, very happy that the initiative could be right now initiated as a result of the grant support offered by one of the premium institutions of our country, that is NIT Suratkal. So it's with great pleasure that we are all seated here from all over Kerala, perhaps all over the country, waiting to listen to the resource persons and perhaps incorporating the lessons that we are learning today in our day-to-day course delivery sessions. So welcoming everyone, as also hoping that the session will give light to our various doubts with respect to such an initiative, with respect to having the virtual labs, a sort of a replacement for our ordinary labs. Sort of, that's all. I conclude, and with your permission, and by sending the message of our principal, as also with quite a lot of pride and privilege, and with your permission again, I declare the initiative open. Thank you.
Thank you, ma'am. Next, I would like to invite the resource person Beryl Thomas to take over the session.
Yeah, thank you, ma'am. Thank you very much. I hope I'm audible. Yeah. Thank you, and a very warm good afternoon to all the respected faculty members of Vidya Academy of Science and Technology. And first of all, I would like to extend our gratitude to the principal, dean, vice principal, all the HODs and faculty members for giving us this opportunity and letting us share this share the insights about virtual labs with you all as a part of this session. Especially in that matter, I would also like to mention that I am a former student of your computer science HOD Ramani Bai ma'am. I hope ma'am is also listening to this session. So in fact, I am a previous student of RMS. And
Yes,
yeah.
well, I'm really excited
Yeah.
to see you here. Please continue. Sorry.
Yeah. So we will be what we will be doing through today's session will be we'll be introducing virtual labs in our perspective, and also we will be looking at virtual labs specific with regard to each department. So we'll be taking a few examples from all broad areas, all departments as such. So that will be what we'll be doing today, and I'll now switch over to a presentation. I'll switch off my video. In fact, my internet is also seeming to be a little unstable. I hope I'm still clearly on. Vishnu sir or anyone, can I get a feedback if my screen is visible and my audio is clear as well?
Yes, sir. You are clear.
Both are fine. Both are fine. Okay, Beryl, both are fine. Moreover, are you in right now in Kerala?
Yes, yes. I'm right now at my home at Kottayam.
Yeah, that's even much better. Okay, so yeah, the screen is very clear, but then perhaps
my colleagues will be. Yeah, and my colleagues will be joining from Karnataka and even Delhi, I suppose.
no, you can go to the full screen mode if possible. That may be better. Yeah.
Yeah, I'm actually sharing my browser window, ma'am. That's why it is a little bit smaller, because I'll be switching over to my other browser tabs as well in as I go forward.
That's fine. That's fine. Okay, please.
Yeah, thank you, ma'am. So to introduce virtual labs, it's an initiative by the Ministry of Education, Government of India, under the National Mission on Education through ICT. So this mission might be already familiar to you all. Even if virtual labs is something new to you, the various other initiatives under NME ICT like Swayam Prabha, the NPTEL MOOCs, the eYantra initiative for robotics, 4C initiative, digital library initiative, spoken tutorial, the various research tools under InflipNet. All these resources are funded under NME ICT, and virtual labs is much like them. And specifically, it focuses on the practical component of science and engineering education, rather higher education. So the basic objective or motivation of creating virtual labs in the first place was to account to the needs of the students who could not really afford to get access to the privilege of getting enrolled into educational institutions with top-notch facilities. So this was actually, this initiative was conceived way back in 2009, and it has been around for over a decade right now, even though it has gained a sort of a prominence or a added relevance as a result of this pandemic when everyone was shut out of their labs. So it was initially created focusing on the needs of students who could not really get into institutions with a sufficient amount of infrastructure. And also, even in case of institutions with sufficient amount of infrastructure, we always have the issue of pace, place, and period. So 3P labs, creating a sort of a 3P labs was the objective of this virtual labs initiative, that is to create a learning resource that works at the pace, place, and period of the learner. So again, it's just learner, not every student or teacher. You don't necessarily have to be a student or a teacher enrolled to some institution also to be a user of this tool. You just can be anyone who's curious to learn. That's the philosophy of creating such a resource. It's a completely free to access, barrier-free web-based tool as such. So coming to the pace part of practical education, whenever we have practical courses or practical subjects, labs in our regular academic programs, when things were normal before March 2020, we used to have them in our labs in our for our practical sessions for maybe 3 hours in a specific week. That time may not be really sufficient for some set of students, at least for some students who find it difficult to grasp the concepts right, or it might be too much for some other students as well. So that pace factor, accounting to that pace factor, and also obviously you have to be at the lab, and you have to be there at the time when the lab is open from 10 to 4 or 9 to 5 or whatever it is, and that is even impossible right now. So this is what virtual labs tried to undertake. It was trying to be an anytime anywhere lab that is free to use, that is accessible from any device that you have with an internet connection, and it was tailored to be made in a self-learning mode with theoretical information, practical simulation. So whenever we say virtual labs, you can obviously assume that it is a simulation-based component where you simulate or provide animated versions of what we normally do or perform in our real labs. So we have that alongside theoretical information, and we have self-evaluation techniques. So as of now, we have self-evaluation techniques. This pandemic has forced us some demand for proctored evaluation modes also, and the consortium is actually working on creating something like that. But as of now, we have some basic self-evaluation tools that learners can try out while performing the experiments to make sure that they have got the theoretical concepts as well as the practical concepts right. And also when you have a virtual simulated variant, you obviously have the freedom to make mistakes. You just like you learn driving on a simulator, and when you learn driving on the road, you have the liberty to make mistakes when you are on a simulator, and you can try out innovative things or otherwise things that are prone to be risky when you're performing experiments in the real labs. And also, as of now, in fact, more than 125 labs across 9 broad areas, specifically for 7 areas of engineering and 2 basic science areas that have been created and deployed on the virtual labs portal. And whatever labs that have been created, so it's an evolving process. As I told, it's a 10-year-old project, and there were initially labs or simulations that were created on earlier web technologies, and even some proprietary technologies were also used. So all of those dependencies and requirements like Flash and all, which has reached end of life recently. So all such requirements were gradually being phased out, and the project is completely migrating over to free and open source technologies right now. And coming to the types of virtual labs, we will be focusing on this specific variant, that is the modeling and simulation based labs, where the simulations are created based on the theoretical or mathematical concepts behind a practical experiment. So that will be programmed behind a simulation, behind a digital animated version of the experimental apparatus or whatever circuit or whatever it is, and you'll be performing the experiment on that digital simulator. So the closeness to reality factor, obviously you'll have some drawbacks in that perspective. You'll obviously not be able to experience those error components that you may otherwise be encountering when you're performing experiments in the real practical laboratories. But when you have nothing as a replacement or as a add-on resource to rely onto or look upon to, this can be a add-on version. And we have 2 other types of labs also, measurement based, where we use data sets obtained out of real experiments. We'll be using those data sets at the back end of the simulation, so that it will be slightly better in terms of closeness to reality, but then the scalability will be limited because the number of input-output conditions will be limited to the number of data sets that the developers would have otherwise created. And then there's a third type called remote triggered labs, and remote triggered and also virtual reality based labs is something that we are working right now on a pilot basis. We'll be trying to demonstrate a couple of examples in these lines. So in remote triggered labs, what we are doing is we are providing web-based access to real experimental apparatus located remotely. So in our case, located in the labs of NITK Surathkal, located in our center those experimental apparatuses are given remote access via a web interface, and the learners will be able to access those resources via online mode and perform their experiments. That's how remote triggered labs have been configured. Obviously, it is very limited in terms of scalability, because when you have a real apparatus, obviously like real experimental apparatus, you will be able to access it only one at a time. Only one person will be able to access it, and also the cost of building and maintaining something like that is humongous, unlike creating a web simulation, which will be accessible for any number of people depending on the server capacity, obviously, at any given point of time. So that is the variance of virtual labs conceptually. And quickly comparing physical and virtual labs, it's obviously costing an institution, teacher or learner nothing to make use of this resource, because it is completely built by Government of India's funds and deployed free to access for anyone. And it is designed for 24/7 usage, and also it is designed for safer use of safer attempts of innovative experimentations. And then obviously we have the problem with user experience. When we will be using simulators, you'll obviously miss the user experience of using performing experiments on real experimental apparatuses. But then obviously in this present situation, the second best option is all that we'll be getting to use for a longer period of time. Even if students are able to come to the colleges to perform experiments, that will be for a very limited amount of time, at least for 1 or 2 more semesters. So for that period at least, in addition to the lab resources, in addition to the lab experiments that they're performing in the labs, this can be an add-on resource. And even otherwise, teachers can use these simulations to demonstrate the concept, demonstrate how things work in their theoretical classes, whether it is online or offline. The simulations can be used to demonstrate things. So these are all the ways in which virtual labs can be used. And coming to the administrative setup of this initiative, it is funded by NMEICT, as I mentioned before, and it is driven by a consortium of 11 participating institutes, and it is led by IIT Delhi, and NITK Surathkal happens to be the only NIT that is involved in this initiative, and we have 6 other IITs, IIIT Hyderabad, Amrita and Dayalbagh universities, and COE Pune. So what these participating institutes do is, as I mentioned before, there are almost 125 odd labs on this platform. So development of these labs, each one of these labs, once we go into the portal, we will be able to see that each one of these labs are developed by one of these participating institutes. And the participating institutes also take upon outreach initiatives like this very workshop that we are conducting today, to make sure that the entire academic community across the country is aware of this resource, how it is created, how it can be used, and also, if possible, how teacher or a learner can contribute to this resource as well. So specific to NITK, we are operating under a transdisciplinary R&D center called the Center for System Design, and we are catering to almost 300 nodal centers like Vidya Academy of Science and Technology across the country, more specifically in South Indian region. And we are also undertaking the development of labs in mechanical and civil engineering primarily, and also we are having some development initiatives in chemical and electrical engineering as well. Also, we have many other transdisciplinary projects in which faculty members, research scholars, project fellows, and project staff from several departmental areas, several domain areas are working, and also we have at times interns from other institutions as well. So we are headed by Dr. K.V. Gangadharan, who is a professor of chemical engineering, and the VLab development is coordinated by Dr. Prithviraj Umesh, who is an assistant professor of water resources and ocean engineering. And in all these projects that the center is undertaking, we have people from all domain areas who are working on a transdisciplinary mode to make sure that all the activities are done and set up in place. And during this pandemic, we also created some add-on video tutorial resources. So in fact, there are video tutorial resources specific to many of these 125 labs that I mentioned before. And we created some extra tutorials for the labs that are developed by NITK, and it is published as part of our YouTube channel, and also it is published in our RT or local website as well. So to the links to all these tutorials, we will be sharing it in course of our session. So with this, I'll end the introduction and I'll switch over to the website itself. So I hope my website screen is visible. Can I get a feedback, sir?
Yes, sir, it's visible.
Yes, sir.
Yeah, thank you. Thank you. So this is the homepage of the VLab central portal. So the URL is vlab.co.in. This is the main address you will have to take note of to access this resource. So you have all the background information mentioned over here. And as we scroll down, you can find the 9 broad areas of virtual labs that we mentioned about earlier, and the participating institutes as well. And you can click any one of these broad areas and you'll be taken to a list of labs offered in that particular broad area. So I clicked computer science and engineering, and I was taken to a list of labs offered in the broad area of computer science and engineering. And alongside the name of the lab, you have the name of the participating institute that has developed it also. So in computer science, most of the labs are contributed by IIIT Hyderabad, with a few offerings from other IITs as well. This is the general structure of any domain page, any broad area page on the VLab portal. And if you go inside any one of these labs, I'll choose to go inside a simple lab, basics of HTML. If I go inside any of one of these labs, I'll get some general kind of headings. So we'll have an introduction, general introduction about the subject, some general objectives. You'll have the list of experiments. And if you go inside any one, inside the list of experiments, you will find a specific number of experiments. Here we have 10. So in some cases, you may have 8, you may have 12. The number might vary from one lab to the other. So anyway, you'll have multiple experiments within inside each virtual lab. And once you go inside the experiment, you will find headings that will look similar to the headings that we normally write in our record books, aim, theory, procedure. So instead of the data analysis or experiment part, you will have a simulation. So the digital simulation will be what the experiment performing part will be, the experiment simulation. And you'll have also some add-on evaluation tools, like we have a pre and post test. So before attempting the experiment, after going through the theory, you can attempt a pre-test and then proceed and perform the experiment and attempt a post test as well. So all these are static tests, not really proctored evaluations. So you have additional reference resources, etc. as well. So as I told before, it's tailored as a complete learning management solution with theoretical material, experimental simulations, and add-on self-evaluation tools and add-on reference materials as well. So in some cases, you have video tutorials, additional learning materials such hyperlinked to the page as well. Sometimes NPTEL lectures also will be hyperlinked, etc. So this is the general overview or general structure of any lab, irrespective of which department or which broad area you will be going into. And the look and feel may be different from one lab to the other. So this is the standard template of the look and feel that is adopted recently by the consortium as a whole. So some of the older labs, if we go into some of the older labs, you'll be finding that the look and feel will be slightly different, but the options will be more or less the same. And the contents will again be following the pattern, like you have the theoretical material, the experimental simulations, and the self-evaluation techniques. That pattern will remain consistent, even though the look and feel, the layout, everything, the template is slightly different also. So this is a general overview about the Virtual Labs portal and the Virtual Labs website. So if you go into any other department also, you will find a similar list of labs, and parallelly you will see the name of institute, participating institute that is developed. This is, and some you will be seeing it as upcoming labs or labs under development or labs under maintenance, you might find over here itself. So this is the general structure. And coming to navigating the portal for labs, looking for labs, we have already shared you a curriculum mapping, a draft curriculum mapping of KTU's curriculum alongside the circular that was sent by KTU. I hope many of you might have already referred to it. So that was a draft reading of our reading of KTU's curriculum, which may not be really comprehensive as such. But definitely you can look for the subject areas, look for the labs that you need, you'll be handling for your students or you're working on for your research, etc. by navigating through the portal like this. And sometimes you may find overlapping in terms of the broad areas. So if you take the example of electronics and communication and computer science, you may find that some of the labs that are relevant for electronics and engineers like VLSI and signal processing, you will find it listed under computer science. And you'll find many labs like network technologies, then many digital electronics labs, computer organization labs, many such resources will be listed under electronics communication. So this kind of overlappings might be there for various departments. Likewise, mechanical and civil engineering, you may find several overlapping subject areas. For electrical and electronics, you'll find many overlapping subject areas. So you may have to look through the list of offered labs in related broad areas as well whenever you are searching for a particular subject. And in addition to this main central portal, another link over here that is called New Lab Development, which will take you to the developer portal of Virtual Labs Initiative. So if you click New Lab Development, you will be taken to a different portal called VLabs Dev, and it is hosted by IITB because IITB is coordinating the overall development activity of Virtual Labs Initiative. And here you will find under Explore Labs, two lists of labs, labs under development and approved labs. So these are labs that are yet to be published to the main website. So these are in different stages of development as well as evaluation. So labs under development will be the resources that are still in different phases of development. So the number of experiments will be limited, or the number of functionality might be slightly limited, but whatever has been developed, whatever has completed development will be available for use. And approved labs are those labs that have completed development but yet to complete all phases of evaluation before getting published to the main website. So if you go into any one of these lists, you'll find that they are not segregated according to departments. Okay, it's taking a little bit time to load. So they are not segregated according to departments, but yeah, you'll find them listed like this over here. So labs from all domains are listed together. You see the name of the department, broad area, and the name of the labs listed together here. So these are approved labs. So all of them will be available for use. They are all accessible. They are all functional, although they are not published over to the main website. And also at times you may find that some of the older versions of labs. So if you take the example of computer graphics, the version that is available over here in the central portal, along the labs that are being offered, the version that is available over here is actually Flash based. So Flash, as you all may be knowing, reached end of life earlier in February this year. So the Flash version is no longer going to work, even though there are workarounds for making Flash versions work. We are phasing out, in the process of phasing out Flash-based labs. So some of the Flash-based labs are yet to be phased out, and replacements are yet to be published. So for those labs, some workarounds may have to be still used. But for the others that have completed the revision or revamp process, so for this Flash-based lab, you have a replacement under approved labs. So this version is HTML5 based, and this is actually replacing the older version. So likewise, you'll have replacements, you have advanced versions of existing labs, etc. also, and also you have completely new subject areas included as well. So this is the general idea of the VLab portal and how to navigate the portal for looking for your subject areas of interest or subject areas that you will have to handle. So this was about the intro of how Virtual Labs project is designed and how it has been put forth. So now we will gradually move on to specific broad areas. So we'll start looking at examples of experiments or labs from specific broad areas. So I'll start off with computer science and engineering. So in computer science and engineering, we saw the list of labs offered over here. And here, as I mentioned before, we have some older versions and newer versions of labs as well. So like computer graphics, we have even data structures, which is also replaced by a new lab. So here also we have an upcoming labs title. These are all actually labs that have completed evaluation and published over to the website. So these are, since they are new, I think I lost my connection in between, sorry. Hello?
Yes, sir, you are audible.
Hello, sir. Ipo audible ആണോ? Hello, Vishnu sir. Am I audible now?
You are.
Yes, sir, you are audible.
Thank you, sir. Sorry for the slight issue. I had a glitch with my network. Sorry. I'll restart sharing my screen. Okay, so I hope I was audible until this stage when I was talking about data structures labs. Can someone confirm that?
True. That's right. Yeah.
Yeah, thank you, sir. Thank you, ma'am. So in computer science, hello, I think there's a participant's mic that is unmute. Hello. Yeah, okay. I hope I'm audible still.
Yes, sir. You are audible.
Yeah, thank you, sir. So in computer science, coming to the subject in general, it's slightly paradoxical because except for the hardware-based labs or electronics-based labs, for most of the other subject areas, we generally don't really have a need of creating simulations because almost all the labs are, after all, virtual itself. You have all the programming papers where you will be performing experiments on a computing device itself with the necessary system software or compilers or IDEs or whatever software that is required for that. So you'll have to make all the configurations on your device and perform the experiments, write the programs, compile it, run it, and run your practical labs on your devices itself. So what is there in addition to that for computer science students on a virtual platform? So earlier I started off by showing HTML lab, so which is one of the basic labs in computer science, which even learners from other domain areas are also interested in for the purpose of placements and all. So in basics of HTML lab, here just as we start, like I said before, we have theoretical information. Then you have the list of experiments. So in the list of experiments, we have 10 here. When you go inside the experiment, you will have aim, theory, detailed theoretical descriptions will be there. And then the procedure. So whenever you hear procedure in a virtual lab, it is the procedure to use the simulator. It will not be the procedure to execute the experiment on a real lab setup. It will be the procedure to execute the experiment on this virtual platform. And you'll have the simulation along with all these steps. So performing the experiment on a virtual platform, it's not really a difficult thing because you'll be having step-by-step instructions, procedure, everything to perform that experiment. So here also in HTML lab, these are things we may otherwise do with the help of our normal IDs or whatever development platforms that we will be using. So you have a text box here. You can write your code in this write code section, and you can see the preview of your result of the HTML code that you're writing, the result over here. So that is easily executable in comparison to what we may normally otherwise write on our system. We'll have to write it on a text file, or we'll have to use an IDE to write the code and execute it by opening it and using a web browser. That's what we normally do in case of HTML. Here, in addition to the provision to write the code, you'll have much more instructions. You'll have all the details about the different tags. You'll have all the details of how to use it. You'll have some instructions. You'll have to write the code according to those instructions and execute it, see how it is working. So that is the way in which you can learn the language, learn the programming language clearly along with using this simulator or writing code on this simulator. So we have multiple other labs also, just like HTML. So here what we are doing is we are replicating that activity of writing code, which we otherwise used to do offline, on our system softwares to an online simulator. So you don't have to have any additional dependencies. You can write it on your web browser. You have the instructions to write the code on the web browser. You have the complete package to learn that language over here. Just like HTML lab, we have Java, Python. Then under development, we have even PHP labs and a few other labs also. So most of these computer science labs follow this kind of a pattern. So it will have the programming language. You can write the code, and you'll have the supporting materials, supporting theoretical materials and syntax information, everything step-by-step instructions to write those code, use those simulators within the lab itself. Even database DBMS is all tailored in this kind of a format. And then there are some other subjects that are more like theoretical than programmatical, programming kind of a subject, like data structures, for example. So data structures, as I told, in the main list, you have a flash-based version, which is getting replaced by the newer version. So this will be the one you will be supposed to use. So in data structures lab, when we go inside, you have a similar kind of a structure. You have the list of experiments. Here we have these many experiments in the first part. So it is divided into part 1 and 2. Together, there are around 15 experiments, I think. And once we go inside an experiment, so here again going inside bubble sort, the headings are more or less similar. We have two parts inside bubble sort, simple bubble sort and optimized bubble sort also. And there is a special lesson on analysis part as well. So the algorithm analysis part is also specifically discussed as part of this simulation. Okay, I think there is a maintenance going on with this particular lab. Okay, I just switched over to a different experiment that was merge sort. So bubble sort I think was under maintenance, which was why it was not working, which will be up back in a little amount of time. So in data structures labs, in almost all the experiments under data structures, the general overview is that it is discussed as a completely theoretical lab. It is not linked with any specific programming language. It is discussed as a completely theoretical lab where the algorithms are discussed with the help of video tutorials and visualizations. So the visualizations will explain the algorithm. So here in merge sort algorithm, we have the aim concept, the algorithm itself explained with the help of a video tutorial, and you'll have the written algorithm also in plain English language. Plain English language algorithm will be there. And you'll have the visualizations on how the algorithm will perform sorting. And you'll have some simulations that will let you practice the sorting algorithm. So here it is slightly different from what we saw for in the case of HTML. So we have a setup and we can use these buttons. Following these instructions, we can use these buttons to see how the algorithm will be implemented on a given set of numbers. So this random set of numbers, it was self-created by the simulator itself. And you will see how the merge sort algorithm will divide this main array into subarrays, perform the sorting process, and then merge these subarrays back to the main array. So that's the whole idea of merge sort algorithm. So that is demonstrated with the help of a simulator. And then you have an exercise chapter also where the user or the learner is himself supposed to apply merge sort on the given test condition. So by way of this, you are supposed to learn the algorithm clearly. And again, the algorithm analysis part is also there, where the time and space complexity, stability, all these things are discussed, and also the comparison with other algorithms. So here in this case, since it is a sorting algorithm, the comparison with other sorting algorithms is also discussed. So with the help of simulators as well as with the help of video tutorials as well. So since this is one of the newer versions of virtual labs, and it is a theoretical lab, it has quite a lot of video tutorials also involved. It will be helpful for even first-time learners who are into learning these different algorithms. So this is how data structures labs, all the labs that are listed in data structures part 1 and 2, all the labs are designed in this kind of a format. So you can even have a look at the other algorithms as well. All are designed in the same format, and even cryptography and computer graphics that I mentioned before, which is listed under the labs under development lab. All these labs are also completely theory oriented or algorithm oriented. It is not linked to any specific programming language. You're supposed to learn the different algorithms, the different data structure algorithms, cryptography algorithms, graphics algorithms with the help of these simulators. So these are the different ways in which labs are deployed in the computer science domain area. And there are other variants also. So in computer networks labs and all, it's a semi-theory, semi-practical kind of a design. So you can have a look at the different other labs that are also offered in computer science, and further use them for the subjects that are compatible with your classroom activities and syllabi, etc. So with this, I will stop the presentation from my end, and I'll hand over to my colleague, Ms. Shrestha, who will be taking you through simulations from the different circuit domain areas. So thank you all. Shrestha. Hello, Vishnu sir. Can you just check if Shrestha has joined or not? I saw her. I saw that she has had joined earlier. I think I cannot find her now. Yeah, Shrestha, you're there.
Yeah, good afternoon, sir.
Yeah, you're audible. You can take over.
I
Shrestha.
think there is slight network interruptions. Yeah, so let me know if there is any break or happens.
Yeah, thank you, Shrestha. Over to you.
Thank you, sir. Very good afternoon to one and all present over here. Myself, Shrestha, working as Senior Research Fellow, Center for System Design and ITK Surathkal. So let me share my screen. Thank you, ma'am. Just a second. I hope my screen is visible.
Yes, ma'am.
Thank you, sir. Yeah, so Beryl sir has already taken you with the introduction to virtual labs and has taken you with few of the experiments in the computer science and engineering domain, right? So today let me take you with few of the experiments under circuit domain labs. So objectives, philosophy, salient features have been discussed. Then these are the broad areas in which virtual labs have been developed, and these are the participating institutes. So before getting into the labs in circuit domain, I would like to repeat 2 points that has already been stated by Beryl sir. One thing, here you can see there are 2 domains relating to circuit. One is electronics and communication. One more is electrical engineering. But other than these 2, you can also find labs relevant to our domain in the relative domains as well. So when we say circuit domain labs, it could be present under electronics and communication, computer science and engineering, electrical engineering, also under physical sciences domain in this virtual lab platform. And one more thing, same concept might be demonstrated under multiple labs. So whichever interface we feel convenient, we can pick that and utilize as per our requirement. Okay, so with these 2 points, let us get into the labs. So again, when we speak with respect to circuit domain labs, you can categorize the experiment into 3 different categories. Okay, so first category you can generalize as, so very basic one, where circuit will already be rigged up. We just need to vary the input parameters and note down the output variations. That is basically for understanding a concept. Okay. Second category of experiments you can find where we will be manually rigging up the circuit and then proceed with the experiment. So it is basically for a practice purpose, and then a similar procedure will follow. Third category of labs or experiments exist where we manually get the components to workspace, rig up the circuit, and then proceed with the experiment. Okay, so today let me show you 1 or 2 experiments for these 3 categories of labs. So firstly, I'll take you with a lab under electronics and communication. So if you look into the list, you can see labs from very basic topic to very advanced ones. So to start with, let us look into one of the very basic lab, irrespective of the domain, basic electronics lab developed by IIT Kharagpur, one of the older labs, and see one of the experiment over here. The lab structure would be similar for each of the domain. So you'll be having introduction, list of experiments, instruction, technology used, and these are the subsections you'll find within each of the lab in any of the domains. So our area of interest mainly would be on the list of experiments now. So these are the experiments listed under basic electronics lab. So first 3 are theoretical based, explaining us the concepts of RLC. From 4th, we have experiments to do. So let us look into one of the experiments. I'll take you with the rectification experiment. So again, inside each experiment, the content covered would be similar. So we will be finding theory for the concept. Then would be the procedure to do the experiment in this virtual lab platform. Then would be the simulation where we actually do the experiment. Then would be the quiz set of questions to test our understanding levels. In some case, it would be pre-test and post-test. Then are the reference links. Also, in some of the simulations, we'll be having additional buttons as well. So for example, this involves oscilloscope. So virtual oscilloscope tutorial, how it has been given over here, it is presented in this particular section, oscilloscope tutorial. Okay, so now let's get into the simulation. So again, we have 2 variations. So let us first look into the very basic one. So, and this is how half-wave rectifier experiment simulatory interface looks like. Here we have the brief instruction or procedure to do the experiment. Here is the circuit that has already been rigged up. This is the simplified CRO interface. Below are the CRO controls. Here are the formulas that could be used to do the experiment or to do some of the calculations. We have simple calculator provided within the simulator itself, which we can utilize it. And here peak current value will be displayed. Okay, so to start the experiment as per the instructions, first we need to set the load using the slider. Then we need to on the experiment by clicking the on button provided over here. Next step would be to provide input to the circuit by clicking on the sine wave button. Then to observe the output in CRO, we can click on the oscilloscope button. Okay, so these are the steps we need to do. Here we just need to vary the RL. Then next step would be to on the setup. So once we on the setup, we will not be allowed to vary RL. So if you want to again vary RL, we need to off the setup and then again reset set RL value to our required one. Okay, so once we set a particular value, we need to on the setup. Next is to provide input. So to observe sine wave in CRO, we need to once again click on the sine wave button. And now to observe the output in CRO, we need to click the oscilloscope button. Okay, so this is the output for the experiment. Now As what we see in our usual physical CRO, here also we have an option to see both the input and output waveforms. So for that, we need to click on the dual options. We can shift waveforms, so we can change individual Y position. We can also change the frequency. We can change the amplitude. Okay, so these are few of the CRO variations or CRO controls available within the interface. Here are the calculation formulas. Here also there is a direct link for oscilloscope tutorial. Okay, so this is one of the simple simulator interface that is available with respect to the circuit domain experiments. So let me now go back to the main list of labs under electronics and communication, and let us see one more lab similar kind of interface where circuit will already been rigged up. So for that, one of the concept which directly comes to our mind when we speak circuit domain labs is circuit solving, right? So we come across many labs, many theorems, many laws to solve a circuit. So does there any lab exist for that? Yes, we have 3 labs explaining various theorems. So 2 are available over here. One is Analog Signals Network and Measurement Lab from IIT Kharagpur. One more lab we have called Electric Circuits Lab from Amrita Vishwa Vidyapeetham. And there is one more lab being developed that is available in the new lab development site. Okay, so let us look into one of them. So this is the simplest one, developed by IIT Kharagpur, again one of the older labs. So going to the list of experiments, these are the list of experiments available within Analog Signals Network and Measurement Lab. So let us look into one of them. I'll take you with Thevenin's theorem experiment. Again, we have theory, procedure, operating environment, quiz, reference, and simulator. So let us get into the simulator and see how it looks. Okay, so this is how we have simulator interface for Thevenin's theorem experiment. This circuit might look a bit complicated, but it is the same circuit as what given in the theory section. So the same circuit has been implemented in the simulator interface as well. Okay. Now here is a brief procedure given. This is the circuit to solve. We have 3 different cases. Below we have the observation table to note down the values. So here also the circuit is fixed. We can just change the input parameters and note down the output variations. Okay, so you can see there are 2 switches, S1 and S2. This is to control input supply and load to the circuit. So case 1 is to solve the circuit in a normal circuit solving procedure, that is by connecting input supply and load to the circuit. Whereas case 2 and case 3 deals with Thevenin's theorem. Okay, so connecting power and load to the circuit by clicking on the simulate button, we will be getting the load current across the load resistance. Now we can go to case 2A. So it is to find Thevenin voltage. So we know to find Thevenin voltage, we need to remove the load. So I'll make S2 as intermediate and keeping S1 in power state. If I click on simulate button, we'll be getting VTH. Now case 2B is to find Thevenin resistance. So I need to short the supply. So my S1 will be short and S2 will be power. Clicking on the simulate button, we will be getting the Thevenin resistance. And case 3, we have VTH, we have RTH. So to find load current using Thevenin's theorem, we just need to click on simulate button. Now we need to compare the results if they are matching. So for that, we need to click on fill data to the table. Then we can observe values being tabulated below. Okay, so this is the load current obtained without using Thevenin's theorem, and this one using Thevenin's theorem. So both are matching. So this is the first set of observation we got for these voltage and resistance values. Okay, so now we can change individual component value as per our requirement and solve the circuit. So this particular experiment or all the experiments under this particular lab is mainly oriented for the practice purpose. Okay, here with each of the experiment, we can create 60 different questions providing different component values. We can solve the circuit using pen and paper, and compare our results coming over here. Okay, so this is one type of simulator interface available for the circuit domain labs. So now I'll go back to the main website of virtual lab. So all the experiments with this kind of simulator interface will have a similar simulator flow. Okay, so now let me take you with one of the lab under electrical engineering. And here also under electrical engineering, you will find wide variety of labs that are core relevant to electrical engineering domain, also that are common to the other domains as well. Okay, we have virtual high voltage lab, industrial electric drives lab, electrical machines lab, PLC, and so on. So when we say electrical machines lab, we have three again, one from COE Pune, one more from IIT Guwahati, and we have a newer lab from IIT Roorkee. And now I'll take you with a newer lab from IIT Roorkee. Okay, so going into the list of experiments, we have 8 being listed over here. So let us see one of them. First one is again theoretical based, explaining the apparatus used in the lab. So I'll go with say 2 or 3. I'll go with the third experiment. And again, we have other sections being similar. I'll directly get into the simulation. And this is how the simulator interface looks for the experiments under this particular lab. Okay, here we have the components. We need to manually rig up the circuit and then proceed with the experiment. So we have many labs with experiments with similar simulation flow. So to name a few, one of the examples, say analog electronics lab, that could be found under labs listed in under electronics and communication domain in virtual lab platform. So experiments within analog circuits lab or analog electronics lab also have a similar experiment flow. Okay, so how will be the flow? First is we need to rig up the circuit. Next, we need to check if the connections are right. Once we have the right connections, we need to provide input, vary them in steps, note down the output for each of the input values. So we'll be getting an observation table. Then finally, we need to go for plotting the graph. We can observe the graph. Then we can finally take a printout of the entire simulation window and keep it for our future references. Okay, this will be the flow. So here we have the instructions given. So first thing is we need to do the connections. So let us quickly do A to K, A to Y, A to J, A to K, A to Y, A to J, then B to P, E to M. So B to P, E to M, F to D, G to R, H to I, just give me a second, G to R, H to I to C, C to H, and there is one more, Q to L. So these are the connections involved for this particular experiment. You can see all the node values being given in blue color. So if you want to remove one of the connections, say you have connected wrongly, then you can click on the node values. So if I want to remove all the connections connected to A, then I can just click on A. If not, if I want to remove one of them, I can click on, say, if I want to remove A to J connection, I can just click on this J value. Okay, so that particular connection will go off. So once we rig up all the connection, next is to check if the correct connections are provided. Once we have right connections being done, we can proceed further. To proceed further, we have 2 inputs here for this particular experiment. One is to set the voltmeter reading by varying armature resistance value. We can, or by first we need to on MCB. Just a second, system is handled. Yes, I have turned on MCB. So the next step would be to set the voltmeter reading by varying the armature resistance value. Once we set it to some value, next step would be to vary field resistance value in steps. Okay, so for each of the field resistance value, we need to click on Add to Table. So each experiment will require certain value to be noted down. Say, for example, if I take few of the reading and then go for plotting the graph, it will ask, please take at least 6 readings. So here, since the platform is virtual, there is no limitations with the boundary conditions. We can provide any value from minimum to maximum. Once we have sufficient readings being noted down, we can go for plotting the graph. Finally, we can go for taking the printout of the entire simulation window, which we can save and keep it for our future references. Okay, so this is one kind of simulator interface or simulator flow we have pertaining to circuit domain virtual labs. Okay, so now let me go back to the main website of virtual lab, and let us see one of the lab under new lab development site. So other than these two, we have many more labs relevant to circuit domain available within computer science and engineering as well. So to name one, computer architecture and organization lab is one, where we have many experiments relating to flip-flops, cache design, CPU design, K-maps, algorithms, and so on. So which you can go into later on. Also, we have image processing lab and others being listed over here. Okay. And also under physical sciences domain, we have, to name one, we have a solid state electronics or solid state physics lab, which again have experiments relevant to circuit domain. Okay, fine. So other than this, there is one more section where we can find many labs available relevant to our domain. That is under new lab development site. And under explore labs, again, we have 2 approved labs and labs under development. So let me take you with one of the lab under labs under development section. So here you can find many labs relevant to electronics and communication or circuit domain. So I'll take you with integrated circuits lab, which takes us to the third set of category what I had mentioned earlier. So we have 6 experiments currently being listed over here. So let us go to one of them. I'm into inverting amplifier experiment. Yes, it is loading. Let us get into the simulation. And this is how the simulator interface looks. So we have workspace where we need to get all the components. We can set individual component value as per our requirement, do the connection, then proceed with the experiment. Okay, so here we can get component to workspace. I'm providing some random value. Similarly, we can get all the components to workspace. To observe the output, we have CRO available. We can get that also to the workspace. We can select op-amp. We can select input as per our requirement. We have 3 options available. So if I go with the sinusoidal input, again, we need to provide the specifications. Okay, now we can go for doing the connection. So for that, we need to click on connect option available. We can move each of the component by clicking on the move option available. Okay, we can connect each of the component using connect option. We need to click on the nodes. Now all the wires are in blue color. Once we do the checking, if the connections are right, it will turn to green color to get the output. Okay, so now we need to provide input and output to CRO. So for that, we can provide input. We can also provide output. Okay, so once we feel we are done with the connections, we can go for owning the simulation. So if the connections are right, all the wires will turn green and simulation will start running. We can observe the graph using show graph option available. Also, we can observe the frequency response for the circuit. Okay, so this is the third type or third set of simulator interface variety available pertaining to circuit domain labs. Okay, so again, we have many labs listed under approved lab sections as well. So for example, like 051 microcontroller lab, it is not available in the main virtual lab website or under labs under development section. It is available in the approved labs section with currently 3 experiments within that. So its interface is slightly different. We have a small editor where we can write our own code. We can run that. We can go for debug options. Okay, we can observe the output variations and so on. So there are many more labs relevant to circuit domain, which I request you to explore and come up with the queries if any. So with this, I'll stop presentation from my end and I'll stop sharing my screen and I'll hand over the session to my colleague Chetas, who will be taking with the labs under mechanical engineering domain. So thank you. Over to you, Chetas.
Good afternoon, everyone. Shrestha ma'am, I hope I'm audible.
Yes, Chetas.
Yes, sir, you're audible.
Okay, so I'll be sharing my screen. Please give me feedback with that. I hope my screen is visible.
Yes, Chetas.
Okay.
Yes, sir.
So this is Chetas. I am currently doing junior research fellowship in CSD, Center for System Design in NITK Surathkal. Today I'll be demonstrating mechanical engineering labs under V Labs. So as earlier explained by Shrestha ma'am and Beryl sir, I hope this V Lab website is familiar with you people. So I'll be directly going to mechanical engineering area. So if you go to this mechanical engineering area, you can see many labs developed under mechanical engineering subjects like technology CAD, virtual lab, remote virtual lab on automotive system by different universities, IIT Kharagpur, Dalbagh, NITK, Surathkal, COE, Pune, etc. So today I will be taking 2 labs developed under NITK Surathkal. One is mechanics of machine lab and the other one is mechanic dynamics and vibration lab. So first thing. So in the mechanical engineering V Labs, we have followed a standard procedure of having introduction, experiments, targeted audience, course aligned, prerequisites, and feedback tabs here. In the introduction tab, there'll be brief introduction regarding the lab. That is, as you can see, since this is mechanics of machine labs, we have a brief introduction regarding what is static, what are dynamics, what is kinetics, Grashof 4-bar mechanism, slider crank mechanism, and etc. And if you click on the experimental tab, we have nearly 24 experiments developed under this mechanics of machine lab, position analysis of Grashof 4-bar mechanism, slider crank mechanism, Scotch-Yoke mechanism, etc. This target audience gives a brief description about who this lab is made for, like who it particularly targets, and on what basis this courses and the simulation is done, what subjects has to have been referred can be seen in course align. And prerequisite tab gives you the basic requirements before going through this lab, and there's a feedback tab here. So I'll be taking 2 or 3 experiments from each lab and I'll be demonstrating it today. So first, let me take velocity analysis of Grashof 4-bar mechanism. Once you click on the experiment, here again, we have a standard tabs here. Theory tab. This theory tab covers almost all the theory necessary for this simulations. The procedure tab demonstrates the procedure which has to be carried out during our simulations. You can test your skills with respect to theory and procedure. You can take a self-evaluation test here. And we have a simulation lab. And we have assignments which will be based on the simulation done, and the quizzes will be there. And there'll be few videos and reference tabs for extra information regarding the simulations and for better understanding. So I will be directly going to simulations. And as Beryl sir explains, we'll be taking non-flash users. So our simulation tab is divided into 3 tabs. Basically, one is the user interface, one is the variable tab, and one is the control panel here. In the user interface panel, we have velocity diagram, position diagrams, and what the AD is R1, AB is R2, and necessary information is mentioned in this particular tab. So in this particular variables, you can vary the R1 value, R2 value, and you can vary it according to your requirements. And then you can play the simulations, and the visual representation is displayed here. With that, even the velocity diagram is also displayed. Whenever you change the R1 and R2 value, you can see the equivalent velocity diagram at that instant of time. You can also use this tab to change the rotation, clockwise, counterclockwise, etc. So I'll take one more experiment. So I'll take, let us take velocity analysis of Scotch-Yoke mechanism. As I said earlier, there is theory section which gives brief theory required and necessity for this particular simulation. And we have a procedure tab, which is required for the particular simulation. And we have a simulation tab here. And same way, as I mentioned earlier, we have a user visual interface tab here, a variable tab and a control tab. So here you can again vary the crank length. As the crank length is varied, you can see the visual representation of that. And you can also change the omega value based on your requirements. So this way you can vary each variables and try to understand how each variable affects the behavior of a particular mechanism. And if I click on show graph here, you can see the graphical representation of a particular mechanism with these variables. So say if I change the variable here, the graphical representation also changes. And this way this graphical representation and mechanism can be used to analyze the Scotch-Yoke mechanism. You can also change the direction from clockwise to counterclockwise. Say now I vary the crank length, you can observe in this. So this is mechanics of machines lab. Now I'll be taking you to machine dynamics and vibration lab, which is developed by NITK Surathkal. As mentioned earlier, we have the same standard procedures of introduction, experiment tab, targeted audience, course align, and prerequisite tabs. Here we have 9 experiments related to vibrations. Now I'll be taking demonstration of free vibrations of cantilever beam. The theory part also consists of all the necessary equations and theories required for this particular simulations. And we have the procedure tab, as I mentioned earlier. So I'll directly go to simulator tab. Here we have for non-flash users, we have explore parts, and these are experiment part. So in the explore part, you can vary the materials so that here basically you can explore according to the cross section what you require without any constraints. You can vary all the variables for a better understanding of a particular experiment. So let me take a material, aluminium. Let me take C section as cross section area. Let me vary the length, and you can see the length of the rod being varied. I'll vary the damping ratio here. So now when I play this, and if I put the graph here, you can see a particular displacement versus time graph is displayed here. You can also see the variation in the graph when I vary the length, or when I vary the damping ratio here, or when I vary the mass. So this way, this particular experiment can be explored by varying each variable and understanding its effect on the displacement versus time graph and the behavior of the particular experiment. I'll be taking one particular experiment for demonstration purpose. So in this experiment, the material is fixed as steel, cross-section is fixed as I-section, length is fixed. And now when I play the experiment, we can see the visual representation of that happening here. Same way you can choose any other experiment of your choice. So now when I start the experiment, I can calculate the logarithmic decrement of the particular experiment. The length is given. See, I'll demonstrate it again. There seems to be some connectivity issue. Please hold on. Okay, so this particular experiment, so we can see the visual representation of the particular length and damping ratio. Now, when I start the experiment, we can see displacement versus time graph, and here frequency and omega d is also given with respect to this particular value. So I can find damping ratio using the logarithmic decrement. So say I give damping ratio as 0.50 and I can check my answer. So this way I can test my skills, what I've learned, and particular formulas for this particular experiment is also given in the procedure tab, if you can go through that. So all the formulas and necessary equations will be given in the theory tab. So based on that, you can work on the simulation and you can explore the simulation part. So these are the two labs which are developed under NITK Surathkal Mechanical Engineering Labs. And I would like to hand over to Rohit Kushwaha to explain the new mechanical engineering labs that are being developed under NITK Surathkal. Thank you.
Yeah, thank you, Chetan. Now, am I audible?
Yes, Rohit, you're audible. Thank you.
So, my screen is also visible?
Yes, Rohit, yes.
So, so as we have discussed the vibration lab and the mechanics of machine lab, so we can see some other labs also. So we'll check one newly developed lab which has the new user interface, as we have already seen the mechanics of machine lab. So the user interface is different, and if time permits, we can check some other labs from different colleges also. So if we come down over here in the lab, upcoming lab, you can see the dynamics of machine lab by NITK. So as we can see, the user interface is different. So we have but the similar options over here. So we have introduction, objectives, experiment, target audience, organize. So here are the experiments given. So in the mechanics of machine, we have seen the kinematic analysis of O-bar and slider crank mechanism. And here we have the dynamic analysis of the similar. So I hope anyone can go and easily explore these two parts, because that the experiment is very familiar. So let's check some other experiments. So we will check for all the one. So once we enter into the experiment, all the options related to the experiment we can find over here in the left side. So what's the aim? So basically the aim of the experiment is to understand the effect of the speed and the RPM of a roll governor with respect to the height. So that is our main aim of the experiment to understand. And once we go for the theory is as we have seen in the previous experiment also is very similar. So all the theory related to the given experiment and the equations and that will be really handy once we are doing the experiment as well. So then there is a p-test. So instead of self-test, there is a p-test and the post-test. So once the user understands the theory and trying to go for the simulation, we can go through these pre-test questions to get our understanding better. So then there's a procedure that is for the simulation. So let's directly go for the simulation. So let's see the simulation. So as we have seen, so we have the experimental setup in the center. Then there's a variable tab which we can use to explore the given parameters. And then there's in the control. So in the control we can get the graph as well as we can directly go for the experiment. So let's explore the RPM and the mass with respect to height. So over here we can see there's a front view and the top view of a parole governor, which is rotating as we can see like animation. Then there's a free body diagram. So we can check from the free body diagram about the flywheel rotating and the center and height of the wheel and height of the flywheel from the center top. So all these things is given over here. So we can take a better reference from here and we can relate to the given governor. So let's check with the RPM. So currently the height is around 9. And if we increase the RPM. So as we all know, for the parole governor, the RPM is inversely proportional. The height is inversely proportional to the RPM. And as that we can see over here as well, that if we are increasing the RPM, we can see the decrease in the height. And the same with the mass as well. So as we know, because of the centrifugal force exerted on the flywheel, the RPM and the mass decreases the height of the shaft. So because of the external forces. So that we can see over here. So that was the explore part. And after doing this variable changes, we can go for graph. So once we check our show graph checkbox, we can get a given values set of a graph. So that we have the RPM in the y-axis and height in the x-axis. And this is the value created for the particular values that have been set for here. So that is from 100 to 130 RPM and for the height that is from that is 600 to 300. So from here we can check, we can hover our cursor over the graph and we can get a particular value at any particular RPM or height. So now let's go for the experiment. So it's always a good practice after the exploration part, we can directly go for the experiment. And once we come into the experiment, we can see the two experiments given, that is calculation and rating kind of part. So let's check the calculation part. So we are in the calculation part, and in this experiment, we need to find the mass of the flywheel. So we can use the constant variables from here. So the Fm by Vm that was given in the free body diagram, and here is the overall mass, and here is the graph. So from this graph, I can put my cursor on the graph and I can get a value for height and RPM, and I can use all these values to calculate the mass. So let me just put some values and we'll check. So after calculating the mass, we can write it over here, and the simulation will give you the feedback whether the answer is correct or not, and will be given with the correct answer as well. So once we are done with this experiment, we can always reset the experiment. So if we reset the experiment, the variables will change and even the calculation will change. So right now, the simulation is asking us to find the RPM. So again, we can use these constant variables. These constant variables and these are the variables from the simulation. We can take these values and we can find the RPM. So again, we can put some value and we can check our answer, and we can reset again. So every time we reset, we will be given with a different variables to calculate from. So yeah, do multiple number of experiments while doing the calculation part. So once I'm done with the calculation part, I can exit the experiment, and there's one more experiment experiment, that is to identifying the part of the governor. So let's check this option, start the experiment. So once we start the experiment, we can see a picture of a governor, and we need to find the we need to find the correct naming for the part. So again, by this fly ball, which is correct. So this is correct. So we can see a check mark over here, that is correct. If we select something else, we can find the uh, feedback that the answer is incorrect. So we can again go from here. Correct answer. So this was the parole governor experiment. So similarly to the parole governor, we have the Porter and the Hartley governor. So uh, we can check these experiments and can relate to each other, and we can find the difference between each of the governor and what are the advantages and disadvantages of each of the governor. So let's come back to let's try some different experiments. So over here we have a balancing of a master in single plane and a multiple plane. So let's check the single plane. So I'll directly go for the simulation. All the options are similar as we have discussed in the governor experiment. So over here we can see shaft with the two of the markers at a particular link length has been given, and we can see a front and a side view of the experiment. So we can pause it. Once we can pause it, we can find the angle related to each other between the two links and between the plane, and we can play it. We can move it into opposite direction as well. So let me just pause it. Let's check the variables. So in the variables, we have the options to change the masses, that is M1 and M2. So currently we are set for 300 kg. So similarly, we can change the link length. Currently both are 20 centimeter. So change, and same the angle between these two link lengths we can also change. So now if we play, we can see the setup that we have done in the variable tab. Once we are done with our setup, we can go from the control panel. By using control panel, we can go to the next page. And over here, let me pause it first so that we can get the angles. And once I pause over here, we need to balance this particular shaft. So over here, you can see the in the variables, we need to first enter the link length to be balanced by this. So let's say the link length will be, after calculation we can put, and let me put some mark over here, and at what particular angle it will need to be set up so that it will be balanced. So let me submit and let me play. So this is the balance mask that we have added, that is the red color with the link length in a particular P, that is the balance mask. And once we enter that, we can find the correct answer. So over here we can see the balancing mask is this, and the position, the angle needs to be balanced. So like this, we can do multiple number of experiments over here while performing the calculation. So we can again, after doing this, we can again go back. We can make the setup again according to our need, and we can again go to the control panel and we can put the values over here, and again we can submit the answer. We can check whether calculated answer has correct one. So as these two experiments, you can see the other experiments also. So all the experiments have the similarly we can explore the other experiment also. So I'll go back to the mechanical engineering lab page. So from here we can choose our interested labs which we want to explore. So I'll show one experiment from the micro machining lab, so that is from COE Pune. So we can explore quickly this also. List of experiments. From here, select first heating of a material. So over on the side, we can see the aim, test, and all that we have already discussed. So let's go to the simulator in the next page. So over here, so basically the aim of the experiment is to the understand the process of the material removal and to estimate the removing rate of the material. So in the over here we have the control panel, and here we can see the visually we can see what is happening, and we will get the results also over here. So in the type of state we can select heating, melting, or evaporation. So and heat energy also we can import. That is clearly present. And we can play the animation also. And we can once we press the plus button over here, we'll get a material remove over here, and we can see the material removal rate also in this and all the related information. So now we have done the heating part. So let me just select with the same material and the heat energy. Let me take the melting and let's see what will happen. So the material, the volume and the radius removed. This is in the heating and this is in the melting, so which is less than that. Similarly, let's see what will happen if we put evaporation. So yeah, even in the evaporation, the removal rate is even less and the volume is also less. So here we can see the working process, the working piece. Over here we can see the heat is applied over here at the working piece and from point A, and we can see the surface over here and the process of breaking that will be removed from here, and we can understand the advantages and disadvantages of this particular process as compared to the other experiment that has been given in this list of experiments. So there are other material removing and micromachining process on this. So that was some of the few labs from the mechanical lab, and there are other labs also that we can go and explore. So from this, I will conclude my demonstration from mechanical lab. I'll hand over the session to Ashwin for civil engineering.
Thank you, Rohit. Good evening, everyone. I'm Aishwarya Hegde. I hope I'm audible.
Yes, ma'am.
Yeah. So I'll be demonstrating on few of the virtual labs in civil engineering domain. So by now you have a clear idea of what virtual lab is and how to access these labs. So we have to go to the site vlab.co.in, and in there, if you go to broad areas of virtual lab, various domains of engineering where the virtual labs have been developed are shown. So I'll be demonstrating on the civil engineering lab. So when I go to civil engineering domain, so you can see there are multiple labs developed by various institutes. So there are labs developed by IIIT Hyderabad, IIT Roorkee, IIT Delhi. Then there are labs developed by NIT Surat. Similarly, many other institutes. So let's see few of the labs that are there in this particular domain. So let's just start with the strength of material lab. So this particular lab is common for both civil and mechanical engineering students. So here again, the template of the labs will remain the same as it was demonstrated in the previous sessions. So we have to go to list of experiments where there will be the experiments in this particular lab will be there. So here in strength of material lab, there are about 14 experiments. So as you see the experiments, there are experiments related to impact test, hardness test. So in hardness test, you can see there is Brinell hardness test, Wicker hardness test, Rockwell hardness test. Similarly, there are tensile test on various material, compression test on various material. So we'll see a few of these. Let's just start with the IZOD impact test. So again, there is theory, then there is procedure, then there is simulation. Simulation is where you'll be performing the experiment. So before we start performing, we'll just go to a section called procedure and see the procedure. So this procedure is not the procedure to do the experiment. It is basically a detailed explanation on how to do the simulation. So it will give you instruction where exactly you have to click while performing the experiment, etc. So once we refer this section clearly, then we'll go to the simulator and then perform the experiment. So in the IZOD impact test, the objective of the experiment is to find the impact resistance of the mild steel and cast iron. So basically what we're doing is we're measuring the toughness of the material. So the apparatus uses the impact testing machine. So you can see this is the impact testing machine. Then we click on next. So now in the first step, the user is given an option to select the type of specimen. So there are two options. There is cast iron and then there is mild steel. So I'll select one of them, let's say mild steel. So once I select the type of specimen, the dimensions of that particular specimen will be given in the table. We'll note down the dimensions and then click on next. So now in first step, what we'll do is we'll pull the lever so that the hammer will strike the anvil portion. And as of now, there is no specimen placed in the anvil portion. So by doing this, we'll measure the loss of energy due to friction. So we'll pull the lever and allow the hammer to strike the anvil portion. So the loss of energy due to friction is measured as 2 joules. We'll note down this value and then click on next. So now we'll place the specimen in the anvil portion. So since it is an ISOD impactor, the specimen will be placed vertically and the notch will be facing the direction of the hammer. So we'll place it in the specimen. So you can see here in the impact testing machine, the specimen is placed in the anvil portion. This is a zoom view of that. And the notch it is placed vertically and the notch is facing the direction of the hammer. So I'll pull this lever so that the hammer will strike the specimen and then we'll measure the loss of energy during the transit of hammer. So it's about 41 joules. Then click on next. Now we'll measure the energy for failure of specimen, that is 41 joules minus 2 joules. 2 joules is the loss of energy due to friction that we measured in step 1. So we'll calculate the energy for failure of specimen, that is about 39 joules. So we'll note down this value and then click on next. For trial 2, we'll take a new specimen of mild steel. So you can see here the dimensions are given for the new specimen. Click on next. Then pull the lever so that the hammer will strike the specimen placed in the anvil portion. So I'll pull the lever. Then we'll note down the loss of energy during transit of hammer. That is about 56 joules. So click on next. Then we'll calculate the energy for failure of specimen. That is 56 joules minus 2 joules. That is 54 joules. So click on next. Now again, we'll repeat the same steps for new specimen of mild steel. So click on next, pull the lever and note down the. So what has happened in trial 3 is the test piece was not broken by the striking energy of the testing machine. So this particular trial, the readings will be considered nil and then we'll click on next. So once we're done with the 3 trials, the readings from the 3 trials will be shown in the table. So then we'll calculate the average energy for failure of specimen. That is average of the 2 readings. So that will come up to in the strength of material lab. So going back, as I said, in this particular lab, there are multiple experiments. So you can see here, these are the experiments that are that deals with the universal testing machine, UTM machine. So we can see this later. We'll go back to the main, the civil engineering domain experiments. So here you can see, again, there are multiple labs that are developed. So you can see in fluid mechanics itself, there is fluid mechanics lab developed by NITK Surathkal. Then there is hydraulics and fluid mechanics lab developed by IIIT Hyderabad. Then there's a new lab that is fluid machinery lab. So let's see one of them. Let's say the fluid machinery labs. So when I go to this particular lab, the look and feel of the lab is a little bit different compared to the previously demonstrated lab. That is because these are newly developed labs. So let's go to the list of experiments. So here there are about 7 experiments. So you can see here, most of the experiments deals with the performance characteristics of various turbine and pumps. So we'll see one of the experiments. Let's say performance characteristics of Francis turbine. So when I go to the experiment, the aim is given to conduct a performance test on Francis turbine under various head and speed condition. Then there is an option called simulation where you will be performing the experiment. So here you can see there is a pre-test and post-test. So basically these are quiz questions which the students can take before performing the experiment and after performing the simulation. So we'll go to the simulation and go ahead with the experimentation. So here in the simulation, as you can see, there are 2 options: Francis turbine under constant head condition and Francis turbine under constant speed condition. So before we choose that, so here in the right side, there is an option called pop-up procedure where the students, while performing the experiment, the students can, in case they get stuck at any point, they can refer this section and then continue with the simulation. So we'll select the Francis turbine under constant head condition. So again, the objective is given, the apparatus used is shown. Then there is a section called description where important definition related to this particular experiment will be shown. So we'll read everything and then click on next. So now we'll start the pump by clicking on the green button. So since it is a constant head condition, the user is given an option to select the head. So from the drop down menu, I'll select the head as 11 meter and then click on OK. So now here there's a question popping. Selected head value is constant throughout the experiment. Say true or false. So what we have selected will remain constant. So it is true. So I'll click on OK. So these questions that pop up, that these are added so that the experimentation does not become monotonous and the students are invested while performing the experiment. So click on next. Now open the inlet valve to keep the pressure constant. Click on next. Now for trial 1, will not apply any weight on the pan. For that, we'll calculate the corresponding torque. So the formula to calculate the torque is given. So you can see here that it's a formula and the observation readings are also given. We'll calculate and enter the value. So I'll enter the value. So click on next. Now what we'll do, we'll insert a tachometer to note down the speed of the motor. Since it is a constant head condition, the speed of the motor will vary for every trial. So that is why we'll be inserting a tachometer to note down the speed of the motor. So for trial 1, the speed of the motor is 1750 RPM. So click on next. So now we'll note down the hook gauge reading. The initial and the final readings are noted down. Then we'll calculate the head of water, that is final reading my actual discharge. So the formula to calculate the discharge is given. So you can see there's a formula. So we'll calculate and enter the value. Click on check. So here in the formula, you can see there are some constant parameters like coefficient of discharge, length of the wire, etc., which in case the students don't know, they can refer this section called variables in calculation. So the values will be given directly. You can use these values in the calculation and enter the value. So Francis turbine is it's a reaction turbine. So I'll click on OK and then click on next. So actually, okay. Under Francis turbine constant head, addition of weight increases the speed. Say true or false. It is false. So I'll click on OK. So these questions, in case you give a wrong answer also, the simulation will give you the correct answer and allow you to continue the experiment. So now, based on observations we made in trial 1, we'll calculate these parameters. We'll calculate input power. So I'm entering a random value. Just click on result to get the correct answer. So even in the calculation part, in case you give a wrong answer, the correct answer will be given directly. So we'll calculate the output power in watt. Efficiency is calculated in percentage, that is output power by input power into 100. Then we calculate unit power in watt, unit speed in RPM, and then finally we'll calculate the unit discharge. So click on next. So for trial 2, some weight is added on the pan. So I'll increase the weight on the pan. So for that, we'll calculate the corresponding torque. So I'll click on check. So the torque is calculated, then click on next. Now we'll insert a tachometer for trial 2 and then note down the speed of the motor for this particular trial. It's 1630 RPM. So click on next. Now again, note down the initial and the final reading. And then calculate the actual discharge. So head of water is calculated by, as I said, it is final reading minus the initial reading. So it's click on OK and then click on next. So now for the observations we made in trial 2, we'll calculate input power using the formula. Output power given by 2 pi NT by 60, where N is the speed of the motor for this particular trial and T is the torque calculated for this particular trial. Similarly, we'll calculate efficiency in percentage. Unit power is calculated in watt given by output power by square root of H cube, where H is the constant head that we are maintaining, which was selected in step 1. Then we'll calculate the unit speed in RPM given by N by square root of H, where N is the speed of the motor and H is the constant speed. So finally, we'll calculate the unit discharge in meter cube per second. Click on next. Now we'll increase the weight on the pan furthermore. Then we'll calculate the corresponding torque. So click on next. Now finally insert a tachometer, note down the speed of the motor for trial 3, it's 1580 RPM. Then note down the hook gauge reading. The initial and the final readings are noted down. Then calculate head of water and actual discharge in meter cube per second. So Francis turbine is located between high pressure water source and low pressure water exit. So click on OK and then click on next. So finally for trial 3, We'll calculate input power, output power in watt into 100, and then unit power, unit speed, and then finally we'll calculate unit discharge. So once we're done with the calculation of all the 3 trials, we'll stop the pump by clicking on the red button. So click on next. Now we can increase the number of trials by increasing the weight on the pan. So as of now, we have increased the weight up to 3 kgs. So you can increase up to 5 kgs and add few more trials for your experimentation. Then for Francis turbine and a constant, that is efficiency versus unit speed, unit power versus unit speed, and unit discharge versus unit speed. So this was one of the experiment in the fluid machinery lab. So let's just go back. So as I said again, there is surveying lab by IIT Roorkee. Similarly, there is structural analysis lab by IIIT Hyderabad. Then there is transportation engineering lab. So basically it deals with experiments related to testing of highway material. So there are about 8 experiments in this particular experiment. So again, there is environmental lab. So in environmental engineering, there are 2 labs, environmental engineering 1 and environmental engineering 2. Similarly, there is marine structure lab, mining geology lab. So if you see marine structure lab, if we go to list of experiments, there are about 7 experiments. Most of them deals only for the first 2 deal with the marine engineering based experiments. Then the rest are similar to the concrete technology lab. So let's see one of them. Let's say slump test. So the aim of the experiment is to determine the workability of concrete mix and to obtain the quantity of aggregates for the given mix. So we'll go to the simulation directly. So the objective of the experiment is given. Then there is apparatus used is shown. Then there's a section called description. So we'll once we read all that, we'll click on next. So the first step is to measure the volume of the slump cone that we are using. So the dimensions are noted down. The formula to calculate the volume of slump cone is given. Then we'll calculate and enter the value. So difference in the radius of the slump cone from bottom to top is 5 centimeters. So I'll click on OK. So click on next. So now what we'll do is in step 1, we'll fix a mixed proportionality ratio. So it is fixed as 1:2.7:4.2 and the water cement ratio is assumed as 0.43. For that, we'll calculate the cement content that needs to be taken. So the formula to calculate that is given. We'll use the formula and calculate and value. Similarly, the quantity of fine exhibit is measured. So once all these quantities are measured, we'll then take a weighing machine and then measure all these quantities. So we'll take about 1.6 kgs of cement as per the calculation and about 4.3 kgs of fine aggregates. So the measurement is done using a weighing scale. Then we'll take about 6.7 kgs of coarse aggregate based on the mixed proportionality ratio we fixed. These are calculated and entered. So we'll take about 0.67 liter of water based on the water cement ratio we have fixed. Mixed proportionality used in the experiment is 1:2.7:4.2. So click on next. So now what we'll do is we'll take all these ingredients, that is the coarse aggregate, the fine aggregate, and the cement that we measured in a pan and mix it using a trowel. So by mixing it, we'll form a dry mix of these materials. So the quantity of cement used in the experiment it's about 1.6 kg. So click on next. So once the dry mix is formed, we'll add the measured quantity of water to the dry mix and then mix it using a trowel. So the mixing is done such a way that there is no lump formation in the concrete mix that we are preparing. The quantity of fine and coarse aggregate taken is 4.3 and 6.7 kgs. Now we'll place a slump cone on the horizontal base and fix it to the base. Click on next. Now we'll transfer the concrete mix that we prepared to the slump cone. So the transfer is done in 4 layers using a trowel. So the first layer is being transferred. And once we are done with each layer, we'll compact the concrete mix using a tamping rod. So the compaction is done by giving about 25 number of evenly distributed blows to each layer. So now we are transferring the second layer of the concrete mix. And compacting it using a tamping rod. Now again, the third layer is transferred. And the compaction is done using a tamping rod. So compaction is done so that there is no air voids that is present in the concrete mix. So finally, the final layer, that is the fourth layer, is transferred. And the final layer is compacted using a tamping rod. The purpose of tamping is to obtain uniform compaction in order to avoid voids. Say true or false. It is true. So I click on OK and then click on next. So we'll remove the excess amount of concrete that is present on the slump cone. Each layer of the mix is tamped for, as I said, it is 25 number of times. So click on next. Now we'll detach the slump cone from the horizontal base by moving it in the vertical direction slowly. Then we'll measure the difference in the height of the slump cone and the slump that we have formed. So the slump value will come up to 18 centimeter. Here is a question. Height of the slump cone is 30 centimeter. So click on next. So for the mixed proportionality ratio we fixed, the slump value is 18 centimeter. So this was one of the experiment in this particular lab. So as I said, there are multiple labs which you can explore in the free time. Including the other than simulation based lab, this virtual lab of the this virtual tour of the labs that are available in our institute. So if you go to this website rtlabs.nitk.ac.in, there's an option for virtual tour of this experiment. During the pandemic, all these lab studies became virtual. So the virtual tour was added. So if you go to strength of material lab, so as of now, there are only 3 labs which has virtual tour. So this is the strength of material lab in NITK Surathkal. So for students who have never come to the campus, or for the students who have been to campus and never been to this lab, once they're studying this experiments, they can get the virtual tour of the lab facilities that are available in the institute. So you can see the facilities that are available in this particular lab. So you can get a 360-degree view of the experimental setup that are available. In addition to that, you can, since we've seen the simulation of the impact testing machine, we'll directly go to the impact test. So this is the impact testing machine. So you can see here. So this is where you'll take the reading. So the students can get an idea of how the experimental setup will look in real. Then this is where you'll place the specimen. This is the annual portion. If it is isoid impact test, the specimen will be placed vertically, and if it is a Charpy impact test, the specimen will be placed horizontally. So you can get different views of the setup also. So you can see here. This is where the hammer will rest. For isoid impact test, it will be resting at 90 degrees. And for Charpy impact test, it will be resting at 270 degrees. So this is where the hammer will be at for Charpy impact test. So you can see here, there's the specimen that is used will be shown. This is the notch of that particular specimen. So similarly, there are the virtual tour of different experimental setup is also shown. So there's a 360-degree view of the experimental setup also. Here there is an option to go to the simulation of this particular experiment. Then there is a link to that connects to the Lagupata video of this particular experiment. So by giving all these facilities, the students will get a complete idea of how the labs will be in the normal mode of education. So I'll just stop my presentation here. Now we can have a quick question and answer session. All the participants, they can either unmute themselves and ask their doubts, or they can put it in the chat box.
Yeah, thank you, Aishwarya. Vishnu sir, we are done with the presentations and demonstrations from our end. So we can take any queries or questions from the participating faculty members at this point.
So we will wait for 5 more minutes so that participants can ask any questions if they have. 2 more minutes.
Sareshta, if you're there, I think you have a question regarding PLC labs in electrical in the chat box.
Sir, can you please demonstrate that PLC timers?
Hello.
Yes, Sareshta, you're audible. Hello, yes, Sareshta, you're audible.
Hello. Am I audible now, sir?
Yes, you're audible now.
Yeah, thank you, ma'am. Yeah, thank you, sir. Actually, under PLC lab, currently there are no there is no simulation for the experiments listed. But there are many experiments relating to timer in the other labs, that is under analog electronics lab, integrated electronics, integrated circuits lab, and so on. So you can refer the other labs for timers experiments, timer related experiments. So under PLC lab in under EEE section, if you get inside the experiments, there are no simulation tab currently given over there. So that particular simulation was dependent on the Flash plugin. So alternate lab for that will be coming up soon. Yeah, thank you.
Yeah, generally regarding Flash-based labs, there is a alternate workaround which we have shared via email. It's a detailed procedure. You can also see it in the announcements tab on the VLab homepage. Within the announcements, you can find a link saying click here to download VirtualBox. So there is a image of an Ubuntu 14.04 version which is customized with necessary plugins to run these labs that were based on obsolete dependencies. So until their replacements are developed and published, only a few labs are left. I think probably 1 or 2 labs in every domain might be there that are yet to be fully replaced with HTML5 or any new technology labs that were earlier built based on Flash or any other dependencies. So such labs, in case of necessity, you can use that particular workaround to make use of those labs. So I hope that point is clear. That detailed procedure is there on the website, or it can be found in, we have also communicated it via email to the nodal coordinator. Vishnu sir, I think you have already received that.
Yes, sir.
Yeah.
Yes, yes.
So any more questions from any of the faculty members? You can kindly come online, turn on their mics or post their queries in the chat box. Sir, if there are no more queries, I think we can go on to wind up the session.
Okay, sir. We can wind up right now.
Yeah. So one thing to
now
add
I
from our
invite.
slide. Yeah. Sir, one thing to add from our slide will be that whatever we demonstrated today, they were just sample experiments. We were just showing examples from all the key department areas. So we would urge and request all the faculty members to explore through the list of labs that are offered on the portal and find out those experiments, those labs that are relevant and useful for the subjects or courses that you're handling and for any other purpose for that matter, and make the maximum use of those labs for your classes, and also encourage your students to explore the catalog of resources on this platform so that they can use it even for self-learning, even if they are trying out or exploring some technologies or subject areas outside their curriculum. They can make use of the resources that are available on the VLAB platform. So kindly make sure that all the students are also made familiar with this platform and the catalog of offerings on the VLAB portal. So if you have any queries, you can always write to us through the non-coordinator. You can always contact us. And our email ID can also be circulated, sir, with all the faculty members.
Sure.
So that's all from our side. Thanks to the management, principal, all the HODs, and the nodal coordinator for taking this initiative to host us for this session, and for all the faculty members who attended from our end. So thank you. Now over to you, Vishnu, sir.
Okay, thank you, sir. Thank you, sir. Thank you for the informative session. Now I invite Ms. Neenu Thomas, Assistant Professor, Electrical and Electronics Engineering Department, to deliver the vote of thanks.
Hello, am I audible?
Yes, ma'am.
Okay. Gratitude is the attitude of soul. It's the time to express the deep sense of gratitude to one and all. Very respected principal, vice principal, our dean academics, executive director, resource persons, HODs, other dignitaries, and participants of this webinar.
Yes, ma'am.
Good evening to all. In this auspicious occasion, the duty assigned to me is to propose the vote of thanks to those who gathered in this knowledge hub of virtual platform. First of all, let me express our sincere gratitude to the resource persons of the day, Ms. Aishwarya Hegde, Mr. Beryl Thomas, Mr. Rohit Kushwa, Ms. Shrestha from NITK Suratkal, who shared their knowledge about the virtual labs with us and showed some demonstrations. Thank you. Now, let me extend our heartfelt thanks to our respected principal, Dr. Saji CB, who is guiding us with great vision. Thank you, sir. Let me acknowledge our beloved Dean Academics, Dr. Sudha Balagopalan, for your inspiring inaugural session. Thank you, ma'am. Now let me express our sincere gratitude to our Vice Principal, Dr. V.N. Krishnachandran, for your valuable guidance. Thank you, sir. I thank our Executive Director, Mr. Suresh Lal, for being a great support to this event. Thank you, sir. Next, I thank Mr. Shali, who gave the technical support for conducting this webinar in a smooth manner. Thank you, sir. Now, I would like to express my sincere thanks to all the HODs who were with us throughout this event. Thank you. It will be incomplete if I don't mention Mr. Vishnu Shaji, who coordinated this webinar. Thank you, sir. Finally, I appreciate and congratulate all the participants from our college and from other institutions who made this webinar a grand success. Once again, I thank you, one and all. Thank you.